Alright, now we're back in question number 3. Now, to solve question number 3, this is exactly what the question demands. It says, consider the initial value problem, dt equals Ka, and then you're given an initial condition of A naught, that is when time equals 0, the quantity of the radioactive substance is A naught. Now, they said this actually models the decay of the radioactive substance. Now we are told to show that the half-life of the substance is given by this equation here. Alright, now to begin to solve this equation, I'm going to rewrite this initial value problem that we're given. So now what we have is we're given the ADT, the ADT equals Ka equals K times A, and then we also give me the initial condition that when time equals 0, the quantity is A naught. Now we know very well that when we solve this differential equation, all we would have is we'll have A equals A naught e to the power kt. This is what we'll get when we solve the differential equation. But we are told that the half-life of the substance is, we are told to show that the half-life is this. Now, how are we going to show that the half-life is this equation here? Now, the first thing is you need to recall the definition of half-life. The half-life is the time when the quantity of the original material has been reduced to half. So what I mean is, for the half-life now, it says when t equals this, that is the half-life, the quantity at time t would be, this is the original material, the original quantity. It says when time is 0, you have your A to be A naught. So that's the original. So for the half-life, by the time when the time has reached its half-life, A would now be half of its original quantity. So then we are told to find C. That's exactly what the problem asks of us to find. So how do we do that? So we're going to start in a jiffy right now. Now to start, let me pull this up so that we use this to solve our equation. So what we have there is we have A equals A naught e to the power kt. So I'm going to substitute A with A naught all over 2. So what we have is A naught all over 2 equals A naught e to the power k e to the power kt. So we want to find t. Okay, now we're told that our t equals what's the name? Our t equals big T. So instead of writing this, I could write this as A naught e to the power k times big T. So when you divide both sides by A naught, so this one goes off and this one goes off. So you have 0.5 equals e to the power kt. So our aim is to find t. Now how do you find t? So we take the natural logarithm of both sides. So you have ln of 0.5 equals the ln of e to the power k this. So when you take this, then the kt comes to this side. So you have kt equals the natural logarithm of 0.5. So when you do this, this is going to give you, you have t equals the natural logarithm of 0.5 divided by k. So we know that natural logarithm of 0.5 is actually the same thing as the ln of 1 all over 2 divided by k. So this is the same thing as, according to the laws of logarithm, that is the natural logarithm of 1 minus the natural logarithm of 2 all over k. So ln of 1 is 0. So this is going to give us negative ln of 2 divided by k, which is actually what we're told to find. Oh, this is the wrong question. Which is what we're told to find. We're told to find that t equals negative ln 2 all over k, which is exactly what we have just proved here. That is t equals the negative ln of 2 divided by k. So we're going to be doing B. Now for part B, you're told to show that the solution of the initial value problem of part A can be written as a of t equals a naught 2 to the negative t all over big T. So you observe this is big T. So the first thing is in part A, we obtained the half-life, or we proved that the half-life was negative ln of 2 divided by k. This was what we had for the half-life. So now from here I could easily obtain my k to be k equals that when you cross multiply you have negative ln of 2 divided by a big T. And then also we recall that when we solved the initial value problem in part A, the differential equation alone gave us a equals a naught e to the power kt. This was what we observed when we obtained the differential when we solved the differential equation. And then now we have our k to be equal to negative ln 2 all over t. So now we are told to find a having known k. So this is going to be a naught e to the power k. Our k now is negative ln of 2 all over big T times small t there. So and then when you simplify that, this is the same thing as we have a naught e to the power. So looking at this closely, when you look at this closely, this is the same thing as minus t all over big T ln of 2, and then this is going to give us a naught e to the power. So we could bring this, that's the coefficient of ln 2 here, we could bring it as powers of 2, so it becomes the ln of 2 to the power negative t all over big T. So this is what we have, and we know a ln of the exponential to the power ln of any number is going to equal the same number. So this is going to give us a naught and 2 to the power negative t all over big T. So this is our value of a. So you compare that, so you'd observe that we had the same thing. A of t equals a naught to the power negative t all over big T, and the same thing here too, small t all over big T. So that's for part B. Now for the last part, it says if a radioactive substance has a half-life t given in part A, how long will it take an initial amount a naught of the substance to decay to 1/8 the original amount? So it says we're going to use the half-life we obtained in part A. In part A, what we had has a half-life. So I'm going to start solution. So in part A, the half-life we obtained was t equals negative ln 2 all over k. This was what we obtained as the half-life. So, and then from here, we can easily obtain k. Our k is going to be a negative ln 2 all over, that's when you cross multiply, all over big T. Now, also in part B, we're able to show that a equals a naught times 2 to the power negative small t all over big T. We're able to show this in part B. Our aim is to find t when a has reduced to 1/8 a naught. In other words, what I mean is we want to find So we want to find small t when a equals 1 over 8 a naught. So that's what we want to find. So I'm going to be using this equation here. So when a equals 1/8 a naught, we have a naught all over 8 equals a naught 2 to the power negative t all over big T. So from here, so we have that this cancels this, so we are left with 1 all over 8 a naught. So now 1 all over 8 is the same thing as 2 to the power negative 3 equals 2 to the power negative small t all over big T. So from here, if 2 to the power negative 3 equals 2 to the power negative this, so this implies that, so going from here now, implies that negative 3 are laws of indices equals negative t all over big T. So but our aim is to find small t. So from here, so we have this crosses out, then this implies that small t equals big T times 3. So this is the time it will take for the initial amount to reduce to 1/8 the original amount, that is 3 times the half-life.